Good afternoon, everyone. I'm Jia Jue from Nanyang Technological University. Today, I'm going to share with you our recent work titled Command Be Served, Parallel Decoding for COTS RFID Tags. This is a collaborative work with my supervisor, Mo Li, and my colleague, Yuanqing Zheng, who is now in Hong Kong PolyU. RFID technology has risen to become a revolutionary and key technology in many areas. Several billions of RFID tags are deployed worldwide in a lot of applications. For example, in marathon races, small tags are attached to participants' shoes to accurately track their time and pace. For another example, items in supermarkets are labeled with tags containing their names and prices, so when customer finishes shopping, he or she only needs to push the cart through a reader to check out. In many of these real-time applications, minimal delay is required. In order to improve RFID network communication efficiency, tag parallel decoding is explored in some recent works. They allow tags to transmit in parallel, and the collision will be decoded. In order to resolve tag collision, some recent works, they formulate the collision as a linear combination of different tag signals and their channel coefficients. Therefore, they require controlled channel measurement to understand the channel coefficients of individual tags. And since they are decoding the collisions bit by bit, they rely on precise tag synchronization so that when tags collide, their signals can align with each other bit by bit. Some other existing works on tag parallel decoding demands adaptive and predefined transmission offsets to separate different tag signals and complex coding to allow tag transmission. In general, these existing works on tag parallel decoding requires extra and non-standard operations at the tag site. Thus, they fail to work if new arriving tags directly transmit their data packets to join ongoing transmissions. And they fail to support commodity off-the-shelf tags, which are already widely deployed in the field. In this paper, we ask, can we enable command be served parallel transmissions without any extensions to COTS RFID tags? The design goals include no extra coordination or communication overhead, and no modification to COTS RFID tags. Before talking about how we can achieve these goals, let's first review the decoding method for one tag. A typical passive RFID tag delivers its information by either absorbing or reflecting reader's carrier waves. So when one tag is transmitting, the signal magnitude exhibits two magnitudes, H for high and L for low. Accordingly, if we look at the two-dimensional IQ plane, we see two symbol clusters representing the two backscattering states. To decode the signals, the reader separates the received symbols into H and L states. Then the binary sequence can be easily decoded. Now we have two tags. As each tag has two transmitting states, we will have 4 states in total, or we say we have 4 symbol clusters on the IQ plane. Similarly, to decode this collided signal, the reader can separate the received symbols into H and L cluster groups. For example, for tag number 1, these two upper symbol clusters represent the H state for tag number 1, and these two lower symbol clusters represent tag number 1's L states. In fact, no matter how many clusters there are on the IQ plane, we can always divide the symbol clusters into 2 groups if we only look at one tag's transmitting states. And for tag 2, we have a different separation, of course. In this paper, we term this process of separating symbol clusters into 2 in terms of one tag's transmitting states as bipartite grouping. And the scheme proposed in this paper is called BiGroup. The point here is, if we can perform bipartite grouping for each tag, we can decode the collision using a conventional single-tag decoder. So this is a basic principle of bipartite grouping. It is, however, challenging in practice. To understand the challenge, let me first show you how signals add up in theory. This is tag 1's two states, H1 and L1, tag 2 states, H2 and L2. When two tags collide, their signals add up linearly at the reader side. So we have L1, L2, L1, H2, so on and so forth. Because of the linear addition property, these four states create a parallelogram. Thus, in this case, we can easily do bipartite grouping in this way for tag 1, and in this way for tag 2. In such ideal cases, we observe linear dependency among these four symbol clusters. However, in practice, we also observe cases like this, where we see no linear dependency among symbol clusters. We hypothesize that is because when multiple tags coexist, tags may backscatter the backscattered signals from other tags. Thus, the same tag channel coefficient may be different in different collision states. And according to our measurement study, such nonlinear dependency becomes more obvious when more tags coexist. We note that this nonlinear dependency is not under control of the reader. Therefore, we have to perform bipartite grouping without purely relying on the location of symbol clusters. How can we do that? Let's look at the time of cluster transitions. We classify each symbol into a symbol cluster, and then we plot the symbol clusters along the cluster label along time domain. And we see during transmission, the symbols move among different clusters at certain time points. We can easily detect this time of cluster transitions. Since our goal is to decide which symbol clusters belong to which of the H and L states, so a natural question is, can we find the time when symbols move between H and L states, which are actually included in this time of cluster transitions? If the answer is yes, then we will know which symbol clusters belong to which state, and then the tag can be decoded. Based on that, we make one observation on data agnostic state flipping. This is one segment of transmitted data bits, and the states to deliver these bits. These red arrows indicate the compulsory state flippings at bit boundaries. In fact, for the reader to track tag's backscatter frequency, a tag always changes its transmission states, either from H to L or from L to H at bit boundaries. And these bit boundaries are the time of H and L state transitions that we have been looking for. So task now is to extract bit boundaries for each tag, and then we will know the time that this tag moves between H and L states. Then we can decode this tag. So how can we extract bit boundaries? The opportunities of doing so lies in the tag unsynchronization. Firstly, different tags respond to the same reader query at different times. For example, in this figure, two tags respond to the same query command, and we see the first tag starts transmitting here, while the second tag starts transmitting here with a delay. To better understand the response delays, we randomly choose 9 tags of the same batch and measure their response delays. Experiment results show the starting time offset can be up to 30%. Secondly, different tags have different bit durations. In this figure, 2 tags transmit the same alternating data sequence. We see they align at first with each other, but as their bit duration difference accumulates along time, these 2 signals gradually become misaligned with each other. Experimental results show the bit duration offset can be up to 1% for each bit. In a nutshell, because of such tag diversities, different tags' bit boundaries do not completely coincide with each other. This may be considered harmful in some previous works on tag parallel decoding. Nevertheless, it will be leveraged in our work to extract bit boundaries. These are the mixed bit boundaries, which are the detected cluster transitions. For one tag, the bit boundaries can be represented as starting time plus 1 bit duration, 2 bit duration, 3 bit durations, so on and so forth. And this is one set of one tag's bit durations. To extract them, we search over a limited range of starting time and bit durations, and then we find the pair of starting time and bit duration which best matches one subset of the overall detected cluster transitions. And this subset will be output as the extracted bit boundaries. Now we have bit boundaries, let's put it together to see the workflow of BiGroup. With the collided signal sequence, BiGroup first cluster the received symbols so that each symbol is classified into one symbol cluster and marked by the cluster label. Then, based on the cluster label sequence, we can find the cluster transitions. Then we extract respective bit boundaries for each tag. After we know the bit boundary of one tag, we can divide the symbol clusters into two groups in terms of that tag's transmitting states. After that, the collided signal sequence can be translated into a binary sequence, and this binary sequence can be decoded using a conventional single-tag decoder. So this is how BiGroup works. Let's look at the performance. We implement BiGroup in the RFID reader based on USRP N210 software-defined radio. We use this reader to read various types of COTS RFID tags and as well as programmable tags. For more information about this testbed, please refer to our Open RFID lab. Let's first look at the performance of decoding tags that runs the standard C162 protocol. In this experiment, we let these tags transmit their data packets in parallel, and we try to decode all the packets. We compare our group with the LA-based scheme in when 3, 4, and 5 tags transmit in parallel. Here, the LA-based scheme decodes collision based on the linear dependency. Therefore, we see in all these cases, BiGroup largely outperforms the LA-based scheme. Overall, BiGroup is able to successfully decode 11 times more concurrent transmissions than the LA scheme. EPC C162 protocol is the de facto and most widely used RFID communication protocols all over the world. In its tag identification process, the reader will require the tags to randomly choose a slot and transmit their RN16 packets. When multiple tags choose the same slot, their packets will collide and the slot will be wasted. BiGroup is applied here to decode the collision so that the reader can acquire the RN16 packets without any overhead. Therefore, with BiGroup, wasted slots will be transformed into useful slots and the identification efficiency will be improved. Specifically, the maximum achievable gain for 200 tags can be up to 6.3 times. And we also observe a consistent gain for a larger scale of RFID tags. In conclusion, BiGroup is the first practical effort to recover collisions for COTS tags in a common be-served manner. To do so, it examines collided tag transmissions at both time domain and physical layer constellation domain and exploits RFID upper layer communication patterns. It is implemented and evaluated on a USRP-based reader that concurrently reads different kinds of COTS tags and programmable tags. Results demonstrate that BiGroup provides direct benefits within the existing RFID communication protocol. Thank you so much for your attention.